Okay, guys, so in this section, we're going to talk about 7.5 and 7.6 briefly. Um, Basically, what we're going to talk about is kind of bringing everything we've learned so far together because the reality of it is that oftentimes we don't really know going into a problem necessarily what method we're going to use. Um, and so we have to have some strategies of like how to look at a integral and determine what method probably is going to work for us. So first of all, essentially integration, as we've seen, isn't as straightforward as differentiation. The reason for this is that when we had differentiation, we had pretty obvious methods that we would use depending on what form the function was in, but in general, we could just derive them. So, if it had a composite function, we chained it. If it had products or quotients, we used product or quotient rule. And so it was pretty straightforward. In integration, though, it's not as obvious. So sometimes, most often our functions aren't really in obvious formats. Um, and also, technically speaking, they're not necessarily integrable. And in fact, many times they aren't in the original form and we have to rewrite it. Okay. So it's actually important to keep in mind that when integrating, there's pretty much only two ways to integrate, and that is U sub or integration by parts. If you can't use one of those two things, then you're going to probably have to rewrite it into a form that will allow you to do one of those two things. But that is the challenge, is recognizing what maybe we need to do. So here's some general guidance for integration. Basically, first of all, we want to simplify it as much as possible, if possible. So cancel things that might cancel, what have you. Okay. The next thing is we want to look for an obvious solution such as basic U sub or integration by parts. I mean, ideally, it's one of those two things. That'd be super cool. But a lot of times it isn't. So the next thing is we have to recognize the integrand by its form. So that is, am I integrating by parts? Is it trig functions, that is like sines and cosines to some power? And if so, which ones? So that is, are they even? Are they odd? You know, things like that. Do we have like sine of, a constant times x and cosine of a constant times x, stuff like that. Um, if that's the case, then obviously we use our trig function methods. If we see something that is like a plus or minus x squared plus or minus a squared, something like that, especially under a square root, then we need to use our inverse trig substitution, or our, um, yeah, uh, basically where we turn it into a theta, then turn the theta into a u, and then integrate it. Um, the next one would be, is it a rational function? If it's a rational, then we're probably going to have to use our partial fraction expansion from 7.4. If we see some radical of a form where it's like a radical and it's just x plus b, okay, then in general, what we want to do is kind of rationalize it. So if we see a square root that doesn't have like perfect squares inside of it, then we're probably going to rationalize it in some way. But essentially, sometimes when you see something and you think, oh, I know a method, and you try it and it doesn't work, well, that's okay. Try something else. Because the reality is that you're not necessarily going to get it the first time. But if you start getting to a point where you feel like you're really spinning your tires and you're just not getting anywhere on that integral, then it's usually a good indicator that maybe your method wasn't the correct move and maybe you should try something else. Assuming, of course, you didn't make any silly mistakes somewhere along the line. So let's take a look at some. So first off, we have something like this. Now, this is not a perfect square. We can't simplify it at all, but it has a square root, and it also has a square root that I think pretty consistently you should recognize from math in general, that if I see a square root, like a fraction under a big square root, then I'm probably going to write it as a little fraction, right? So like 2 square roots, something like this. And if I saw something like this, I'd probably start here. So it's just one of those things that from math, it's just a common math thing. So I'm going to start there. Now, essentially, we don't have a perfect square in here. Mainly, we don't have an x squared. That's the main problem. So we're not going to use our like our inverse trig substitution methods. So instead, we're going to need to deal with this in some way, because like this can't be u subbed and this can't be integrated by parts. So instead, I'm going to rationalize this. Now, the decision on rationalizing is which one do I want to have my square root on at the end of this? And the answer for me is generally I like to have the square root on the bottom. It usually makes it easier than when the square root's on the top for whatever reason. So I'm going to rationalize this, but there's two radicals, so I'm going to choose to leave the bottom in a radical and the top get rid of it. So that is, I'm going to have 3 plus x multiplied on top, and then that means on the bottom 3 plus x needs to be multiplied on the bottom. So we can do this because we're doing the same thing top and bottom. The other thing that I notice about these two things is that they are conjugates, and that's actually a good thing for us, because when we multiply by here, first of all, 3 plus x times 3 plus x, that's squared, and then it's the square root, so it just cancels and we just have 3 plus x. That's nice. And on the bottom, it's also pretty nice because it's going to turn into the conjugate. Essentially, 3 times 3 is 9, or it's multiplying by the conjugate, so it's kind of like a difference of squares. 3 times 3 is 9 minus x squared. And this is all under the square root dx. Okay, now we're going to reevaluate this thing. So we have 3 plus x over square root x minus x squared, or square root 9 minus x squared. Okay, we have a couple options here. First of all, whenever I have a fraction that's separated by plus and minus, I'm going to think, well, maybe I need to write this as 3 over square root 9 minus x squared plus x over square root 9 minus x squared dx. Okay, so that's maybe my first move here. Again, whenever I see a fraction, I'm thinking, maybe split it top and bottom. I mean, it probably makes it a little bit better. Let's say for this thing here, if u was x squared, or even not even that, let's do the whole thing. U equals 9 minus x squared, something like that. Then du would be negative 2x. Now, that is easy to do here. We can easily put that into this thing. So we're going to do that with this one. So I'm going to take them separately. So that is to say, this is the integral of like negative 2. I need a negative 2 here. So that's going to mean I need to pull out a negative 1/2 in front. Negative 2x dx becomes my du. And this becomes 1 over the square root of u. Now this is pretty easy to integrate. So that's good. We have that thing. Now over here, we can't use u sub, we can't use integration by parts, so we're going to have to do something else. Now, if you recall, we had our section on our inverse trig. If we notice something like this, then we should go to that. And just as a reminder of what those things are, let's pull up what we've already talked about. So whenever we have a square root and an x squared, we're going to be using this table here. Now, it is important to recognize these things. So it is something that maybe you don't, in my class, necessarily have to memorize this table, but it is important to at least be able to recognize that that table exists and when we need to use it. So I recognize, I mean, really, I recognized it before I split it up, but I'm still thinking maybe I can split it up to make my life a little bit better. And we did, so that's easy. This one we'll deal with. So we have a constant squared minus x squared, so we're going to use our sign to convert this thing here. So essentially that means that we are going to write for this one. So I'm going to leave this one alone. Let's just focus on this one here. We have that x is equal to a sine theta. Now a here is 3, so 3 sine theta. Okay, so that means that we are going to derive this thing. So dx is equal to 3 cosine theta d theta. So that means we'll replace our dx with this thing here. The other thing that we have is obviously our right triangle. theta. So sine is opposite x over hypotenuse 3. So that means that this right here is square root 9 minus x squared for the base. Okay, so that's useful to know and keep in mind for when we convert back. So again, this is simple u sub, but this one's going to be a little more complicated u sub. So I'm going to pull this 3 out. We have 3 times the integral of 1 over square root 9 minus x squared being 3 sine theta squared. And then replacing the dx with 3 cosine theta d theta. 3 cosine theta d theta. Okay, and again, we haven't dealt with this. We can deal with this at any time. We'll come back to it. Okay, so I'm going to pull that 3 out again, potentially, but if you notice, this right here is the square root of 9 minus 9 sine squared theta. So if we factor out a 9 and take the square root of it, it would be 3 square roots 1 minus sine squared theta, which means essentially that 1 minus sine squared, if you recognize, that's 3 times the square root of cosine squared theta. So squared and square root cancel. And this 3 with that 3 will cancel, and this cosine will also cancel. So we end up with something actually really super nice, and that is the 3 times the integral of 1 d theta minus 1/2 integral of u to the negative 1/2 du. Okay, so notice with this, because we had 1 minus sine squared, that canceled out really nicely with the cosine that we created and to replace our dx. And so essentially, we're just integrating this thing. So let's go ahead and do it. 3 times the integral of d theta is theta minus 1/2 times u to the positive 1/2 over 1/2 plus c. So these 1/2s cancel, and we're left with 3 theta minus u to the 1/2 plus c. Now, as a reminder, what our u is, u was 9 minus x squared. So minus the square root of 9 minus x squared plus c. Now theta, on the other hand, we have theta. We have to solve for it to find what theta is. We have x over 3 equals, so I'm solving for theta here. X over 3 is equal to sine theta, so we take the sine inverse, and we get theta is sine inverse of x over 3. So 3 times sine inverse of x over 3. And that would be our integral. Now, I purposely split this up, and this is actually going to make our life a lot easier. If we hadn't split this up, this integral would be quite a bit more challenging. We'd have to use, we'd still do this, but we wouldn't be able to like cancel everything out. Things would be something we'd have to use some u sub for most likely, or something else. So initially, in this form, it's doable, like we could deal with it, but it's actually much easier to split it up and treat it as 2 separate integrals. And that's just something to keep our eyes open for. Whenever I have a square root separated by plus or minus, that's something that's always going through my head. All right, let's do another one. Okay, so we have 3x to the 15th e to the negative x to the 8th. Okay, now this has all the look of something that's like a product, potentially using integration by parts. However, an x to the 15 means that I'm really not interested in doing integration by parts, because you'd have to do it, 15 times for that to go away. So I'm hoping that there's some other thing available. Additionally, if this was like my x, then this would be my dv, and I don't know how to integrate that anyway. So, but I do notice some things here. X to the 8th, x to the 15th. Oh, wow, those are really similar. If we say like u is negative x to the 8th, then du would be negative 8x to the 7th. 7 and 8 makes 15. So I'm probably going to do something like that, dx. Okay, so I pull that 3 out. This is the integral. Now, I want a negative for this thing here. essentially for my like x to the 8th. So, well, let me show you what I mean. Is if we split this up, this is x to the 7th times x to the 5th, x to the 8th, e to the u dx, okay? So now we have an x to the 8th for our u, but we need a negative here. So if we put a negative, okay, something like this, then we pull a negative out. But we also need a negative 8 here for that. So negative 8. So I'm going to pull out negative 8 here. So we have a negative 8 and a dx and it's x to the 7th. That is going to become du. Negative x to the 8th is our u, e to the u. Integral, that's a positive 3/8. All right, so now this is integration by parts, but it's a lot better integration by parts. So that is u is u. Well, that's easy. So that means du is du. E to the u is our dv. So that means e to the u, and I should say du technically. E to the u du is our dv. So e to the u is our v. So we plug that into our formula for integration by parts, which is something you should remember. Okay, it's necessary for you to remember that one. U times v, so that's u, e to the u, minus the integral of v, that's e to the u, du. So that means we have 3/8 times u e to the u minus e to the u plus c. And so we can start replacing everything and distributing this. This would be 3/8 times u being negative x to the 8th, e to the negative x to the 8th minus e to the negative x to the 8th plus c. And I didn't distribute that 3/8 very well, so I got caught up. So let me do that a little bit better. I multiplied it here and didn't do it here. So minus 3/8 e to the negative x to the 8th plus c, because 3/8 times a constant is a constant. There we go. All right, so again, recognizing, if I choose a u, that's something that I'm also always keeping in mind. If I choose a u, I'm thinking also, what would my du be? So if this was my u, my du would be x to the 7th, essentially. I don't really have to worry about like particulars, negative 8 x to the 7th. I'm really thinking about powers of x's and seeing, would that make it so I can do some substitutions? And yeah, we could. All right. So now we have something here. Now this is x squared square root 9 minus x squared. Okay, so again, if I see a square root here, I'm thinking, well, maybe I'm going to be using some form of the inverse trig, these things here. This is also a product, so maybe I'll end up using integration by parts at some point along the way, maybe not. Eventually we might have something like this, might even be a nice form for like a table, which we'll talk about eventually, but for now we don't have the table. That's 7.6. So let's just get into it. This is again a constant minus x squared. Excuse me, I had to sneeze there. So we have the x equals a, which would be 3 sine theta again. Hey, look, we have another one pretty similar. So that means that dx is equal to 3 cosine theta d theta. We also have a triangle. That was a really poor triangle. Let me try that one again. Okay, theta. Again, its sine is opposite x over hypotenuse 3. So this would be the square root of 9 minus x squared. Now you're going to see why I try to avoid square roots on top. I prefer them on bottom for this. It always seems like, well, not always, but it often seems like these ones are more challenging than when it's on the bottom. So that's why I made sure that it ended up on the bottom. The other reason I made sure it ended up on the bottom is because like the top would then be able to be split open, so split apart. We can't do that on top, obviously, or excuse me, whatever. We can't deal with that if it's still square root here on top. We're not going to be able to do certain things that we could with the other. So that's a little unfortunate, but it is what it is. Okay, now in this case also, I I should note that I'm not going to use u sub, and the reason I'm not going to use u sub is because this is an x squared, this is an x squared. If this was an x, well, I could definitely use u sub then, but because it isn't, no u sub to be had. And we're not integrating by parts because this thing, I don't know how to integrate that. I could derive this twice, we'd have to do multiple steps, but I don't know how to integrate this thing, so we're kind of stuck there. So instead, I'm just jumping into doing some substitution stuff. So we have the square root, so this is integral x squared, square root 9 minus 3 sine squared is going to be 9 sine squared theta. The dx is going to be replaced with 3 cosine theta d theta. Okay. Now, we have everything in theta except for this x, but we don't really have an x squared here. We do have an x, which we can find by squaring it. So that is to say, the integral of x squared becomes 9 sine squared theta. This is the square root. These both have a 9 in common. We can factor that 9 out and take the square root, which would be a 3. Square root 1 minus sine squared theta times 3 cosine theta d theta. I'm going to start combining all these numbers. 9 is 3 squared, 3 cubed, 3 to the 4th, so that would be a 3 to the 4th outside. Integral sine squared times cosine. The square root of 1 minus sine squared, that would be square root cosine squared theta, and that would cancel. So we have sine squared and cosine squared. So we have sine squared theta, cosine squared theta, d theta. Okay. So now we are left with sines and cosines. So that's our 7.2 where we were doing sine cosine things, but this is more specifically a half angle because these are even. We don't have an odd to deal with. So let's pull up a trig cheat sheet real quick. Okay, so we have our half angles. So sine squared is 1/2 1 minus cosine 2 theta. There we go. Let's just pull this up. Okay, so sine squared, I'm going to rewrite in terms of the 1/2 cosine. So this would be 3 to the 4th integral. Sine squared becomes 1/2 1 minus cosine 2 theta. And the cosine squared becomes 1/2 1 plus cosine 2 theta d theta. Okay, so we've rewritten that. This would be a 2 squared. Pull it out. Okay, so on the bottom. So that is 3 to the 4th over 2 squared times the integral of 1 minus cosine 2 theta, 1 plus cosine 2 theta d theta. Now, this thing here is something that we can FOIL. So that we can, and it's a difference of squares. It's a conjugate. These are conjugates of each other. So that's nice. 3 to the 4th over 2 squared. I have to really make sure I'm writing these every step, otherwise I'm definitely going to forget them. So 1 plus cosine 2 theta minus cosine 2 theta cancels, and then we have a minus cosine squared 2 theta d theta. Okay, so at this stage, like, we can split this and integrate this thing here. But this thing here, cosine squared, is an issue for us because it's a squared. And again, we can't deal with it like that. We're going to have to do another half angle. So we have 3 to the 4th times 2 squared times the integral of 1, which is just going to be theta, okay, minus the integral 3 to the 4th over 2 squared times the integral cosine of 2 theta. Now again, because it's an even power, we are going to go to the half angle. So its cosine squared is 1/2 1 plus cosine 2 theta. So 1/2 1 plus cosine 2 theta, but our theta was 2 theta here, so that's actually now 4 theta d theta. Okay, so I can pull that 2 out. So that's 3 to the 4th over 2 squared theta minus 3 to the 4th over 2 cubed. integral 1 plus cosine 4 theta d theta. Okay, so the integral of cosine 4 theta here is going to be just like the integral of cosine. So we can integrate that. We can integrate 1, so we can integrate this now. We have 3 to the 4th over 2 squared theta minus 3 to the 4th over 2 cubed theta, for that integral, minus 3 to the 4th over 2 cubed. So the integral of cosine is sine of 4 theta divided by 4 or divided by 2 squared. Again, I'm just writing them all in twos, so I don't have to do any real math. And then we have our plus c. Okay. So we have 3 to the 4th. I guess at this stage, I'm going to start writing them out as what they are. 3 to the 4th is 3 times 3 is 9 times 3 is 27 times 3. Well, geez, that's why I didn't do it. Let's go to Desmos. I don't trust math in my head, I'll be honest. 3 to the 4th, 81. I should have known that. It's just 9 times 9. Anyway, 81 over 4 theta minus 81 over 8 theta minus 81 over 2 to the 5th. So that would be 8 times 2 is 16 times 2 is 32. Sine 4 theta plus c. Okay, now here is our next issue. And I mean, it's maybe an issue. If we want to clean this up to something reasonable, it's an issue. Sine 4 theta. Thetas we can deal with because of our triangle. Let's go back to our triangle conversion here. So let's have that. Okay, so theta, if we know that sine of theta is x over 3, then solving for theta, theta is sine inverse of x over 3. That's easy enough, no big deal. So we can plug those in here. The problem here is that, like, if you were writing that here, sine of 4 of sine inverse x over 3, like, that's kind of a really horrible way to write that. And so what do we do to make that thing a little bit better? Well, we have to think about sine of 4 theta as sine of 2 times 2 theta, something like that, okay? And we can again go to our trig here, and sine of 2 theta is 2 sine theta cosine theta. So that would be something like 2 sine of 2 theta cosine of 2 theta, something like that. And then we'd have to use that same logic again to try and rewrite these things potentially. So again, a sine 2 theta would be 2, this 2 is still here, times, okay, so this part is where the sine 2 theta is. That's 2 sine theta cosine theta, okay. This cosine 2 theta, well, it's not as nice. So we would have to try and think of something to do with this thing. So I would maybe use this sine here. The reason why I would use the sine is because sine inverse and sine. So instead of cosine 2 theta, I'm going to say 1 minus 2 sine squared. 1 minus 2 sine squared theta. Something like that. Now, if we think about this thing a bit, we'll clean this up a little bit. This would be 2 times 2 is 4. Sine theta, well, sine theta was x over 3. Cosine of theta is adjacent over hypotenuse, so that would be square root 9 minus x squared over 3. Times 1 minus 2 times sine squared. But let's write that. Sine theta squared, like that. That's what sine squared is. Theta, again, sine theta is x over 3. So, this becomes x over 3. So, doing a little bit of more work, this would be 4x square root 9 minus x squared over 3 times 3 is 9 times 1 minus 2 times x squared over 9. And that's all this thing here. So it might not look a whole lot better, I mean, until I were to do some more cleanup. I mean, 9 and 81, that cleans up pretty nicely because, again, I was just working on this thing, but this is all still being multiplied by 81 over 32, something like that. And that's just this part. These and that we didn't really have to mess with too much. So, we have those. So let me go ahead and write those now. I have my plus c. Let's write that, plus c. We have 81 over 4 theta. Theta is sine inverse. So 81 over 4 sine inverse x over 3 minus 81 over 8 sine inverse x over 3 plus something like this. Now again, this 4, that becomes 8. This becomes 9, and this becomes 1. So it cleans up a little bit. We'll just clean this up just a tad more. Plus, this would be 9x square root 9 minus x squared over 8 times 1 minus 2x squared over 9 plus c. And we still have all of this stuff here. So again, it's not like super awesome form, but it's certainly better than writing it in terms of like sine of 4 of sine inverse. Like what the heck would even, like what would that even mean? So we really don't want to write it in that form. Like we don't want to write this as sine of 4 times sine inverse x over 3 because this all is inside the sine. All of this. It's not like sine of 4 times that. And this is a horrible form. So we do have to clean it up. And that's actually one of the issues of running into like these double angles is sometimes you have to do it a couple times or whatever to get it down to theta. Anyway, so again, the integral maybe on this isn't all that hard, but what is hard is all this cleanup at the end. Just to get into a form that's not the worst form in the world. I mean, it's still not good form, certainly not, but it could be worse. All right. Let's do another one. So we have cosine of 1 over x cubed. Okay, so maybe I'm thinking 1 over x is my u, right? So potentially something like that. If 1 over x is my u, that is to say x to the negative 1 is my u. So if we derive this, negative 1 x to the negative 2 is my du, and we need a dx, obviously. So if we rewrite this one to be more like that, that'd be negative 1 over x squared dx is du. Okay, well that's pretty good because we have a 1 over x is u's, that's a 1 over x times a 1 over x squared. So that's actually pretty good for us. Also, if we bring it up to the top, we can see that maybe a little bit better depending on how you want to view it. This is cosine of u times x to the negative 3 dx. So essentially, we have an x to the negative 1 as our u. So if we split this as x to the negative 1 times x to the negative 2 dx, something like that, well, all I need to do is put a negative into this and pull a negative out. And now I can replace everything. So negative integral of negative cosine, or sorry, the negative was placed in there to get rid of. So a negative x squared dx, like a negative x to the negative 2 dx, is a du. So that's just du here. And we still have this x to the negative 1, but that's a u. So this is cosine u times u, like that. So we have u cosine u du. Now this is an integration by parts, most likely. So if we choose u to be u, cosine of u is my dv. Again, thinking because u will simplify, cosine won't, that's why I'm choosing u to be my u. So that means that du is du, and the integral of cosine is sine of u. I should have said this was a du technically, but whatever, we know to integrate with respect to u. So sine of u is v. So we have negative times uv u sine u minus the integral of v, which is sine u, du. All right, so that means we have negative u sine u plus the integral of sine is cosine, but it's a negative cosine. So this would be a minus cosine u plus c. So now we can replace our u's. Negative 1 over x sine of 1 over x minus cosine of 1 over x plus c. All right, so that one wasn't too bad. Again, basic u sub, pretty much, and some manipulation. All right, e to the 4x plus e to the 4x. Okay, so when I see exponents that have sums or differences in them, the first thing I'm thinking here is that we can split it as using our basic exponent rules, where if you have the product, so like a to the x, or let's just say a to the 2 times a to the 3, right? If you have these two things, same base, multiply them together, we get a to the 5th, we add the 2, right? So we can split them into a product then of the same base. So I'm going to split this at that sum here. This is e to the 4x times same base, e to the e to the 4x, something like this, dx, okay? So again, this thing is the exponent, and this thing is the exponent of the same base, e. Okay, and again, that's just using our basic exponent rules. But like I said, if I see exponents with sums or differences, I'm definitely considering that. That's definitely something I'm thinking. Okay, now I'm going to probably stick with a u is this thing here, this kind of complicated thing. So like if I said u is e to the 4x, the nice thing is that du, I mean, first of all, we have e to the 4x, okay, potentially, because that's good, because du is e to the 4x times 4. So dx. So we have an e to the 4x, we have a dx, we just need a 4, pull out 1/4. So we have 1/4 times the integral. 4 e to the 4x dx becomes du. E to the 4x, that's just going to be e to the u. So the integral of e to the u is e to the u. Oops. Times 1/4 plus c. And we replace back with u being e to the 4x. So that is e to the 4x over 4 plus c. All right, so again, you know, this section isn't really technically anything new. It's just recognizing tricks. And so I tried to include any trick that I might think of as potential things. I mean, but the sky's the limit on tricks. There are, algebra little tricks all over the place. And so realistically speaking, people who are proficient with algebraic manipulations excel on these things a lot more than students who maybe aren't super, I don't know, strong in their algebra. And that's why algebra is so necessary, is not necessarily because, the pre-calc did solving exponential equations and solving different equations. The solving isn't really all that important for calculus, since we don't really do much solving of algebra in calculus, but we do a lot of algebra manipulation. So technically speaking, if you are proficient in like pre-algebra math, then you're probably going to be pretty proficient at this. But if you aren't, you're going to maybe struggle to see what can I do. And so that just takes practice. There's really no getting around it. It's practicing these things, trying out different stuff, and just seeing, can I get it into a form that works? All right. So anyway, let's now talk about, can we integrate all continuous functions? The answer is no. Okay, so for example, the integral of e to the x squared dx is continuous. It's a continuous function, but it has no method for finding its explicit integral. So that is to say, we don't really have a method to find an integral of this thing explicitly. So far, the functions that we have been dealing with are what we call elementary functions. They are polynomials, rational functions, power functions, exponential functions, log functions, trig functions, inverse trig function, hyperbolic, and inverse hyperbolic functions. Hyperbolic, as a reminder, are just like your sinh and cosh and stuff, the sine hyperbolic, essentially, rather than sine, cosine, tangent being defined via a circle like we're used to from trig, it's defined using hyperbolas and stuff. So I don't honestly use, like, I don't really use those very often because I don't really see those very often. The trig that I tend to do is based around circles, so I prefer circle trigs. But we do have like tables for those, but that's beside the point. Basically, all functions also that can be obtained from any of these operations, um, any of these things by the 5 operations of addition, subtraction, multiplication, division, and composition, those are what we call elementary functions, okay? And so essentially, if f is an elementary function, then f prime is also an elementary function. But the integral of f is not necessarily elementary. And that's the issue that we have here, is that the integral of this isn't elementary, okay? Um, Basically, we know that because it's been proven that it's not an elementary function, but whatever. So no matter how hard we try, we'll never be able to actually express this in terms of the functions that we know. However, we will be able to express it as an infinite series much later in this book. We'll talk about eventually. But this function really isn't unique. This e to the x squared isn't unique. And most elementary functions actually don't have elementary antiderivatives. So that's a problem, is that like many things don't end up having integrals. We can't integrate them using the methods we know. And that's honestly the struggle. Like, you might think that that seems kind of far-fetched because we're used to every type of equation having some kind of solution in our math. But if you think back to like Renaissance period, in Europe, when they were really interested in quadratic functions, but they didn't yet have a method to solve quadratic equations. So they had to solve each one as an individual. They didn't have one method to solve all of them, like, complete the square, quadratic formula, factoring, etc. They didn't have anything like that. They basically had to come up with a solution to each problem as a unique thing. And that's kind of the case of integration in general. And when you get into differential equations, it's the same thing, because differential equations are just equations using integrals. And so they're made up of integrals. And so like the problem is that while they can certainly fall into families of problem types that like we go, oh, that's this kind of group and we can integrate those groups like this or solve those differential equations like this, there's no guarantee that the problem you have is something you can actually integrate. If you can't get it into one of those forms, then we have to get kind of creative or whatever. We also can use tables and technology. Now, technology is kind of one of those, sore points, I think, with educators sometimes, where we think, we have students who go like, well, I have this program now, like, I remember when Wolfram Alpha was new and people were like worried, like, oh no, Wolfram Alpha is going to make it so that students, whatever, will just be able to do things or what have you. And now you have, I don't know, photomath or something like that. Obviously, as an old man, I don't keep up with those things. But essentially, you may think, well, this technology can solve those things. And the reality is, yeah, the technology actually is usually pretty good at essentially fixing things to tables. So the technology uses the tables that we have, the integral tables, and it just tries to match it to those. And it can usually do it really quickly, right? Because it's technology, it can just run through, doesn't match this, no, doesn't match this, no, doesn't match this, no, etc. And kind of go through the known integrals. But the problem is sometimes when you use technology, it doesn't really give you it in a form that is nice. Also, it's not going to solve anything. Like, it's not going to find the explicit formula for like integral of functions like this that don't have elementary integrals. So it's also still limited by the same things we're limited by. It's just that it can do tables a lot faster than we can. But there's still plenty of value in actually doing these integrations by hand. And honestly, the reason for that is because when you get into higher level math, I mean, it might seem like a bit of a pyramid scheme if you think, well, you need to learn this so that you can use it in a future class. But that's the reality, is that, like, if you're an engineer, you're probably going to go work for some engineering firm if you can pass engineering school. You can, or whatever, get your engineering degree, I should say. You're going to go and work for some engineer that they probably have already programmed Runge-Kutta, which is like an approximation method for differential equations, on something, and they just run Runge-Kutta for a lot of stuff because it's whatever, right? And many of those um, engineers are never using their calculus knowledge because they're relying on the knowledge that somebody else has. And so they had some elder engineer or the really high paid engineer there at work who knows his math and has programmed, or her math, and has programmed those things. And you can kind of like stand on their shoulders, right? But maybe you want to be that person, or maybe you're not going into engineering. If you're going into like math or statistics, I can tell you that we do a lot of integration in math and statistics that is kind of like more theorems and proofs. And so, you're kind of maybe not necessarily having explicit integrals that you're dealing with, or at least not in really nice forms that you can kind of use technology for anyway. But whatever. It's just something to be aware of, is that, yeah, I'm well aware that there's technology, but there's technology for everything, right? And at the end of the day, if technology can do it and you don't know how to do it without the technology, then what purpose do you have in existing at any career or whatever? Like, seem kind of like a redundancy that's not necessary. All right, so let's talk about tables of integrals. Um, as mentioned, the technology uses tables. We have tables. We have some real basic ones, and we have the textbook refers to as a relatively brief table of 120 integrals. There are much more extensive tables that basically contain thousands of entries because, as we've run into challenging integrals that stump people, those people might find the solution to it and then they add it to the table essentially. So, again, standing on the shoulders, right? So here is the book's table of integrals, and like I said, it's 120. So they're kind of broken down into different forms. So something like this, notice we could potentially have gotten some nice stuff out of this. This was something we had just gotten kind of done doing, an x squared, a squared minus x squared. Um, so that's nice. We could have used that if we had it. Anyway, so like I said, there's quite a few, and you can go through those and take a look at those. I'm not really gonna, I mean, it's kind of nice if you know some of these things, um, that they exist. So if you ever get stumped by something, maybe it's in a form that you can go to a table for. That's something that's certainly nice. But on the homework, I will certainly specify, like, go to the table to use to solve this or what have you. Otherwise, it's assumed that you're not using a table. Okay. Or at least not too advanced of a table. Maybe a basic table that's like the first page of this, like these ones potentially, the basic forms. These are certainly basic form tables that you should know and or at least recognize, because like I don't use these ones very often, and so I don't necessarily remember them off the top of my head, but I at least know that they're in the table. Okay, so let's go ahead and talk about like this one, right? So we have sine inverse of square root x. Now the problem is that even though we have tables, they're often not necessarily in a form that we can even use the tables for in that way. So instead, we have to first write them in some way that then we can use the table. So in this case, like we don't have anything with like sine inverse of square roots on the table. You can look, we don't. So if we say like u is square root x, well, if we derive this, then that would be like a 1/2 x over square root x, or 1 over x square root x, and we don't have that. So instead, we're going to rationalize it. So if we call this u squared is x and derive this, we get 2u du is equal to dx, and we replace the dx with this. We'll have the integral of 2u du sine inverse of u. Now, we can pull that 2 out. 2 times the integral of u sine inverse u du, this is something that we can go to our table for. So let's see, we're looking for a u sine. So nope, these are square roots. Nope. These are sines and cosines to some power. These are sine inverses. All right, that's more promising. U sine inverse u. Well, it's that one right there. We just plug this in. And again, nothing special. We just have to use this thing. But again, keep in mind our u is square root x. So when I'm plugging this in, I'm just going to take care of that. So we have 2, and obviously these are over 4. So this 2 times those things over 4 cancels. It makes like 2 on the bottom. So that's what's happening there. So we have 2 times u squared. Our u is square root x. Squared is x, so that's x, minus 1 over 2 times sine inverse of u, that's square root x, plus u, square root x, times the square root of 1 minus u squared, that's 1 minus x, over 2 plus c. Again, just using the table, nothing special. All right, but again, the big point here is that oftentimes it's not in a form we can go to the table with yet, but we can at least get to that stage. Okay, so we have the integral dx over the quantity x squared times 4x, the square root 4x squared plus 9. Okay, so this one here is obviously of a format that we can use inverse trig substitution, which we'll probably do afterwards, just to make sure that the two agree. So realistically speaking, we could do that. We don't have to use the table. The table may or may not make our lives better. Let's see. So if we go to this, we have forms involving square root a squared plus u squared. Keep in mind that u squared is our variable. So we're looking for here, 28. This has a u squared outside. That's important for us. So we have 28. Let me go ahead and just snip that. Bring it into the other page. Okay, so keep in mind that u is our variable, a is our constant. So our order is a little bit messed up. Let me rewrite that. This is the integral dx over x squared square root 3 squared plus 2x squared. Okay, so a few things to note about this. This is not a u squared. Our u kind of is like a 2x. So we have a little bit of an issue here dealing with that. So I find that probably the best move here for us to get it into the format is, rather than thinking about this as our squareds first, let's start by saying this is 9 plus 4x squared, and let's just make it into an x squared so it's a better format. So how do we do that? Well, we factor out a 4. Now you might say, well, 4 doesn't go into 9, but that's okay. It doesn't really matter. We can still pull it out of 9, leaving behind a fraction. So if we pull out a 4, that leaves behind 9/4 plus x squared. Okay, now I'm going to pull this 4 out as a 2, because the square root of 4 becomes 2. So that will come out, and I'm going to move it in front of my integral. So we have integral 1/2 times dx over x squared times the square root. So now this is an x squared and an x squared. I just need to write my a as a squared. That would be 3/2 squared plus x squared. Okay, so now it's the format that we need. So from here we can just throw it into our formula. We're going to have negative 1/2, because this is 1/2, this is a negative, square root a squared. So again, our a here is going to be 3/2. It's squared, so that's 9/4, plus u squared, which in this case is x squared, over a squared again, so 9/4 times x plus c. Okay, so let's go ahead and clean this up a little bit. First of all, dividing by 9/4 is like saying times 4/9. So we have negative 1/2 times 4/9 times the square root of 9/4 plus x squared over x plus c. This will then simplify. This will be a 2. This is a 1. Okay, so we have negative 2 square roots 9/4 plus x squared over 9x plus c. Okay, just a little bit more cleanup because that's kind of an ugly format. We can put this 2 back into our square root. So 2 into the square root, it would be like a 2 squared into the square root. So that is 4. So we have negative square root 4 times 9/4 plus x squared over 9x plus c. So that means then that we kind of get it back into our original format. Negative square root 9 plus 4x squared over 9x plus c. So this is our integral. And so notice that even if our table is seemingly going to make our lives better, a lot of times we still have to manipulate things to get it into a better format so we can actually deal with this. Now let's see what this method would look like without the table, because as mentioned, this should be a format that we can deal with. It looks like a format that we would try our trig substitution for. So we have square root 4x squared plus 9. So this thing is going to be, we're going to use our x equals a tangent theta because it's a plus. Now keep in mind that our x is the whole thing being squared. In this case, our x is not x, it's actually 2x is equal to a 3 tangent theta. Okay, so let's manipulate this a little bit. First into the format that we're used to seeing for x. X is 3/2 tangent theta. We also have, if we solve for tangent, that would be 2x over 3 is equal to tangent theta. That's going to be useful for our triangle. This will be useful for our derivative. All right, let's go ahead and find the derivative. Dx is equal to 3/2 secant squared theta d theta. Our triangle, this is theta. Tangent is 2x over 3, and then this would be 4x squared plus 9. Okay, so let's go ahead and start converting these things over. Integral, our dx is going to be 3/2 secant squared theta d theta over x squared. Our x here is 3/2 tangent theta. That would be 9/4, or since this one's in 3/2, let's go ahead and write it 3/2 squared tangent squared theta times the square root of, in this case I'm going to leave it alone, 4 times our x squared, which would be 9/4 tangent squared theta plus 9. Okay, so a bit of cleanup work. First of all, one of these can cancel. Cool. The 4 times 4 will cancel, and we have 9 tangent theta squared theta plus 9. So I can pull out that 9. So let me do that. This 3/2 on the bottom is like saying 2/3 here. So divided by 3/2 is the same as saying times 2/3. So I'm going to pull it out. We have secant squared theta d theta over tangent squared theta times, so again, pulling out the 9 and pulling it, so factoring out the 9 out of each of these, and then taking the square root of 9, we get times 3 square root tangent squared theta plus 1. Okay, tangent squared theta plus 1 is just going to be a secant squared. Pull this 3 out, that's 2/9 times the integral secant squared theta d theta over tangent squared theta times the square root of secant squared theta. Okay, so squared and square root cancels, and then one of these secants will completely cancel out, leaving on top a secant. So we have 2/9 integral secant theta d theta over tangent squared theta. Okay, now if we choose u to be tangent, then we'd need a secant squared. If we chose secant, we'd need a secant and a tangent. We don't have that. So now let's try and rewrite these things as what they are. So as a reminder, what is secant? Secant is 1 over cosine. Okay, so we have 2/9 times the integral 1 over cosine theta divided by tangent. What is tangent? It's sine over cosine squared for both of these because it's a squared, d theta. Okay, so let's rewrite this. We have 2/9 times the integral 1 over cosine theta times the reciprocal cosine squared theta over sine squared theta. Okay, one of these cosines will cancel, and we're left with 2/9 times the integral cosine theta over sine squared theta d theta. Alrighty, so now if I choose my sine to be u, because it's the most complex part of this, if I say that sine theta is u, then the derivative of sine is going to be cosine theta d theta. That's our du. We have a cosine theta and a d theta, so that's cool. We have 2/9 integral of cosine theta d theta becomes du, and sine squared theta becomes u squared on the bottom, which on top is u to the -2. Okay, now we can integrate this thing. The integral of u to the -2 is going to be 2/9 u to the -1 divided by -1 plus c. So that is to say, our solution here is -2 over 9 times our u here. Our u is sine theta. So this u is on the bottom, so it's sine theta. I could also have called this thing, since it's 1 over sine, I could have also called it cosecant theta. It doesn't really matter, but the u should be on the bottom, so I put my u on the bottom, plus c. Okay, so now let's go ahead and take a look at our triangle that we drew up here. All right, so sine is opposite over hypotenuse. So that is -2/9 times 1 over opposite 2x over hypotenuse square root 4x squared plus 9 plus c. Now, this is why I probably should have just called it cosecant instead of 1 over sine, but because 1 divided by this is like multiplying the reciprocal, so we really have -2/9 times the reciprocal of this, the square root 4x squared plus 9 over 2x plus c, and this simplifies. 2 and 2 cancels. We're left with negative square root 4x squared plus 9 over 9x plus c, which, if you recall, is the same thing that we had on the other one, just in a different order. I wrote my 9 first because that's how the table did it. All right, so it doesn't really matter which method we use. The table can sometimes make our lives better, but you should be careful and make sure that it's in the correct form. All right, so now let's talk about integration using technology. Basically, computers are obviously quite good at matching patterns, so they are quite good at matching integrals to integration tables. Programs like Wolfram Alpha can integrate many functions, but not all technologies give you answers in the same format. They might appear to disagree with each other or with integration by hand. So just because it's in one format doesn't make it not the same as something in a different format, but just be aware that technologies might give you formats differently than what you'd expect. Integration by hand can often lead towards an integral that's in a better form than technology would give us, and obviously it still has value despite technology being capable of kind of integrating these things. Because when you get into higher level maths, a lot of times you don't have nice explicit formulas that you can just throw into Desmos, or Desmos for one, or Wolfram Alpha or whatever. But also you're taking calculus, not how to do calculus on a computer. So, I know that a lot of times when you have students who they go, oh, well, if the technology can do it, then why do I do it? Well, the technology can do a lot of things, so why do you bother doing, cars drive, so why should I like learn to walk and stuff? Uh, I don't know. Maybe that's a bit of a stretch, but you get the idea. And obviously, my whole career depends on you needing to learn this stuff. So, you got to learn it, right? Anyway, so that is our strategies for integration and also using tables and technology. As mentioned, we do have these tables, but oftentimes you can integrate these without. It might be kind of nice to be able to use tables in certain situations, like for example, secant cubed. The integral of secant cubed is kind of tedious to do by hand, and I do it a lot, as you will see in videos, but you can obviously find it on this table of integrals, and it would probably make your life a lot better than having to do that every time. Secant cubed right here, much easier, but it is what it is. So thanks for watching.